Hi friends, this is Naresh. Uh, Here in this session, I'm going to explain about design of connecting rod. I will explain some more problems on design of connecting rod. This is unit number 2. Okay, unit number 2 and subject name is design of machine members 2. That is DMM-2. Okay, this is my lecture number 24. Okay, in this session, I will explain how to solve the connecting rod problems. In this session, I will explain how to determine the whipping stresses, induced in the connecting rod, and also how to design a big end cap, of the connecting rod, and also how to select a suitable bolts for join the big end cap. Okay, in this session I will explain all these topics. First of all, I am going to explain about whipping stresses problem. This is a question. The following data is given for connecting rod. Okay, in this problem, the connecting rod specifications are given. So here, this is a engine speed capital N. You have to consider speed as capital N, 1500 RPM. RPM means revolutions per minute. And length of the connecting rod. Length of the connecting rod equal to 250 mm. Length of the connecting rod is small l equal to 250 mm. Here, length of the connecting rod means the distance between centers of the big end and small end of the connecting rod. Okay, the distance between the big end and small end of the connecting rod is called length of the connecting rod. You have to consider small l for length. Small l equal to 250 mm, and length of the stroke 120 mm. The stroke length means the distance between top dead center and bottom dead center. Okay, the piston moves from top dead center to bottom dead center, bottom dead to top dead center. So the distance between top dead center and bottom dead center, that is a TDC and BDC. Okay, that is a stroke length 120 mm. Length of the crank pin. Here the length of the crank pin 52 mm. Here the big end of the connecting rod, connected to the crank pin. So here the size, the big end diameter, the big end hole. Already we know the shape of the connecting rod. Okay, at the big end, there is a big hole. That is a provision. That hole for crank pin. So that hole diameter is 36 mm. Diameter of the crank pin is equal to 36 mm, and the length of the crank pin equal to 52 mm. Okay, and density of material is 7,800 kg per meter cube. Here the density of material means here we are designing connecting rod. So the material used for connecting rod is maybe cast iron or cast steel or aluminum. Okay, here the density of the connecting rod material is given, that is 7,800 kg per meter cube. Okay, this is the density, that is mass per volume. Okay, mass per volume is the density 7,800, that is rho is the symbol of density, and the thickness of the web or flange is 4 mm. Here this is the cross section of the connecting rod. Yeah, web or flange is given, that means the cross section of the connecting rod is I cross section. Okay, and the cross section of the shank of the connecting rod is I cross section. So that I cross section flange or web thickness is given, that is small t. You have to consider as t equal to 4 mm, and permissible bending stresses in the cap. Okay, here the cap material, The stresses induced in the cap is given, that is 100 Newton per mm square, that is 100 megapascal. By using these details, you have to determine the whipping stresses. Whipping stresses or bending stresses induced in the connecting rod. Okay. So here, by using these specifications, you have to determine whipping stress. First of all, you have to know the whipping stress, whipping stress or bending stress. Here, uh, P. This is a piston. Okay, this is a piston, and this is a stroke line. Okay, stroke line. So that is a TDC and BDC line. Yeah, this is a PC. PC line is a connecting rod. Okay, you can consider as a connecting rod, CP as connecting rod, and OC as a crank. Okay, so when piston reciprocates within the cylinder, uh, then inertia forces develop in the connecting rod, because high amount of pressures are acting on the piston. That's why the due to the mass of the reciprocating parts, high amount of inertia is induced in the connecting rod. Okay, these all are the inertia forces. Okay, this is a uniformly varying load. Okay, you can treat it inertia force as uniformly varying load. This uniformly varying load, here you can observe zero at the piston pin and maximum at the crank. So that is mr omega square. Mr omega square is the maximum inertia force. Okay, so this maximum inertia force, mr omega square at crank pin. Okay, capital C is the crank pin. Okay, now, so here M1 is the mass of the reciprocating parts. That means mass of the piston rings, mass of the piston pin, plus 1/3 mass of the connecting rod. Okay, mass of reciprocating parts equal to mass of piston rings, mass of piston pin, plus 1/3 mass of the connecting rod. Okay, small r is the radius of the crank. Okay, and omega is the angular velocity of the crankshaft. Okay, omega is the angular velocity of the crankshaft. Okay, and now I am converting this uniformly varying load. I treated this uniformly varying load as a simply supported beam. Okay, then then the maximum bending stresses induced in the connecting rod at the 1/3 length of the 1/3 length of the connecting rod from the piston pin. Okay, from piston pin you have to consider 1/3 length of the connecting rod. Okay, at that length, maximum bending stresses may occur. Okay, that's why you have to find out the maximum bending stresses at 1/3 length of the connecting rod. Okay, so whipping stresses or bending stresses will maximum at 1/3 length of the connecting rod. Okay, so the formulas for solving the whipping stresses. Yeah, these are the given data. These are the given specifications. So that is engine speed, length of the connecting rod, stroke length. Ls is the stroke length. Small l is the length of the connecting rod. Length of the crank pin, Lc. Suffix Lc as the length of crank pin, and the diameter of crank pin, dc. Thickness of the flange, I treated as t, small t, for I section. Density of the connecting rod, rho is the symbol for density. Permissible bending stress in the rod, 100 megapascal. 1 megapascal equal to 10 power 6 Newton per meter square. And capital A is the cross sectional area of the connecting rod. Here this is a I cross section. Okay, here the flange thickness is given, flange and web thickness is given. Okay, so that means given connecting rod having I cross section. So the area of I cross section equal to A equal to 11 T square. Okay. Here T, the value of T is given, that is 4 mm. So substitute 4 mm in this equation. Then the area of the cross sectional area of the connecting rod equal to 1.76 into 10 to the power of minus 4. Here 4 mm, I converted 4 mm into meters, that is 4 by 1000. 4 by 1000 equals 0.004 meters. Okay. Okay, this is a 1.76 into 10 to the power of minus 4. This is minus 4 meter square. Okay. By using this area and density, you have to find out the mass of the reciprocating parts. That means mass of the connecting rod and mass of the reciprocating parts. So the mass of the connecting rod, the formula for mass of the connecting rod equal to density of the connecting rod and the cross sectional area of the connecting rod into length of the connecting rod. Okay, this is the formula for mass. Okay, mass equal to density into area into length of the connecting rod. So density, already we know the value of density, 7800 kg per meter cube. This value in meters. Okay, that's why you have to substitute all values in meters. So density 7800 into area also in meters, that is 1.76 into 10 to the power minus 4 meters square. And length of the connecting rod already given in data, length of the connecting rod equal to 250 mm, that is 0.25 meters. So here I substituted all values in same dimensions, that is in meters. Okay, so that's why the mass of the connecting rod is equal to 0.3432 kgs. Okay, so by using this mass, you have to find out the maximum bending stress or maximum bending moment. Angular velocity, already we know the formula for angular velocity of the crankshaft. The angular velocity of the crankshaft omega equal to 2 pi n by 60. The speed of the engine is given 2 pi n by 60. N value is given, that is 1500 rpm. So substitute 1500 rpm, and this is the answer for angular velocity of the crank. Okay, angular velocity of the crankshaft, that is 157.07 radians per second. Okay, after getting the angular velocity and the mass, by using these answers, you have to find out the maximum bending moment. That is M max. Maximum bending moment will occur at the 1/3 length of the connecting rod. Okay, already we explained earlier. So the maximum bending moment will occur at 1/3 length of the connecting rod. So the formula for maximum bending moment for connecting rod, M max equal to mr omega square. Mr omega square is the maximum inertia force. L square by 9 into root 3. L is the length of the connecting rod by 9 root 3. Okay, by using this formula, you have to find out the maximum bending moment. Okay, R is the crank radius, omega is the angular velocity. Already we found that value, and R value already given in question. Okay, here L by 4, crank radius equal to L by 4. That is length of the connecting rod equal to 4 times the radius of the crank. Okay, L equal to 4R. From that formula, R equal to L by 4 equal to 0.06 meters, and M is the mass of the connecting rod. Okay, mass of the reciprocating parts. Okay, so here you can observe C point is the crank pin and P point is the piston pin. Okay, the maximum inertia forces occurs at crank pin, that is mr omega square is the inertia force, maximum inertia force. Now substitute all values in maximum bending moment formula. You will get the answer M max equal to 2.03369 Newton meter. Okay, here the force, here this is a force. So bending moment, the units for bending moment is Newton meter or Newton mm. Okay, So here the values are in meters. So therefore the units for bending moment equal to Newton meter. And ZX is the section modulus. Section modulus, already we know the section modulus for I cross section. Okay, already we discussed in previous class. Okay, so the ZX is the section modulus for I cross section. That value is 13.97 into T power 3. Please, this is a T power 3. Sorry, T 0.004 is the thickness, whole power 3, whole power 3. So this one also uh, T power 3. Okay, thickness of the flange, whole power 3. Okay, 13.97 T 97 T power 3. Okay, okay, this is the section modulus. And whipping stress or maximum bending stress. The formula for already we know the formulas. Bending stress equal to maximum bending moment by sectional modulus. Already these formulas already explained in previous semester. That is MOS, mechanics of solids or strength of material subject. Already we discussed in that subject. So bending stress equal to maximum bending moment by section modulus. Okay, so Z value is 0.89 and 10 to the power of minus 6, and M max, maximum bending moment, equal to 2.03 into 69, 2.0369. Okay, and now maximum bending stress equal to 2.288 into 10 to the power of 6 Newton per meter square. Okay, so bending stress or whipping stress. Okay, whipping stress or bending stress or maximum bending stress due to inertia forces on the connecting rod. Okay, sigma max equal to 2.2 into 2.2 into 10 to the power of 6 Newton per meter square. Okay, this is the answer for whipping stress. Okay, here for now you have to check the maximum stresses. Yeah, the maximum bending stress is 2.288 in 10 to the power 6 Newton per meter square induced in the connecting rod. Okay, but already in our question, maximum permissible bending stress is already given. Permissible stress already, this value already given in our problem. Okay, that is 100 into 10 to the power 6 Newton per meter square. Okay, this is the actual induced stress. This is the actual induced stress. This is a given stress. Okay, so the actual induced stress is less than the given stress. Okay, given stress is 100 megapascal, but the induced stress is 2.2, so it is very less. Okay, yeah, the induced stress is less than the given stress, therefore the design of connecting rod is safe. Okay, now coming to the another problem, that is size of bolts for securing the big end and big end cap. In this problem, you have to find out the suitable size of the bolts. Okay, so this is a bolt and nut. Okay, this is a bolt head. This is a shank or body. This is a nut. Here for join the big end cap, we are using these types of bolts and nuts. So we have to design a suitable size of the bolt. That means you have to design a suitable diameter of the bolt. Okay, so here you can observe the animation. This is a small end of the connecting rod. This is a big end of the connecting rod. So the small end of the connecting rod connected to the piston pin. Okay, this is a piston pin, and this is a big end of the connecting rod connected to the crank pin. Okay, Here this is a big end cap. This is a big end cap. Okay, to join these two parts, okay, we have to use a suitable size of bolts. Here we are using two bolts. Okay, here we are using two bolts for join the big end cap. Okay, so here also you can observe. So to join this upper part and lower cap, we are using two bolts. Okay, these are the phosphor bronze bushes. These bushes acts as bearing surfaces. Okay, in this problem we have to design a bolt. Okay, the question is the following data is given for connecting rod. Okay, the engine speed is 1500 rpm, length of the connecting rod 250 mm. Okay, engine speed means capital N, capital N, that means speed of the crankshaft. Speed of the crankshaft equal to 1500 rpm, and length of the connecting rod. Length of the connecting rod means the distance between big end and small end is the length of the connecting rod, that is 250 mm, and length of the stroke, that means a stroke length. Stroke length equal to 250 mm, that is LS. Okay, that means the distance between TDC and BDC is the stroke length. LS equal to 120 mm, and mass of reciprocating parts 1.5 kg. Okay, mass of reciprocating parts means mass of piston pin, piston rings plus 1/3 mass of the connecting rod. Okay, mass of the reciprocating parts equal 1.5 kg, and the length of the crank pin. Here, this big end of the connecting rod connected to the crank pin. So the length of the crank pin equal to 52 mm. That is equal to width of this big end cap. Diameter of the crank pin, that means this whole diameter, this big end hole diameter equal to crank pin diameter, that is 36 mm. Density of the material, that means the density of the connecting rod material as 7800 kg per meter cube, that is mass per volume. Okay, the thickness of web or flange, the thickness of web or flange equal to 4 mm. Here you can observe the cross section of the connecting rod is I cross section. Okay, so the flange thickness or web thickness of the I cross section equal to T equal to 4 mm. Permissible tensile stress in the bolt is 100 Newton per mm square. Here the stresses induced in the maximum stresses induced in the bolt material is 100 megapascal. Okay, these bolts are manufactured by steel material. So the stresses induced in the steel material equal to 100 megapascal. Permissible bending stress in the cap, that is here this is a cap. The stresses induced in the cap equal to 100 megapascal. Calculate the nominal diameter of the bolts and thickness of the cap, and also determine the whipping stresses. Okay, so by using these specifications, you have to determine the suitable diameter of the bolt and thickness of the cap. This is a cap, a big end cap, so you have to determine the thickness, this thickness, and whipping stresses induced in the connecting rod. Okay, these three values you have to find out. Okay, these are the given data. Okay, by using these details, you have to find out the suitable diameter of the bolt, and also you have to determine the stresses, whipping stresses induced in the induced in the connecting rod. Okay, the speed of the engine N value is given, that is a capital N equal to 1500 rpm, and the length of the connecting rod. Length of the connecting rod means the distance between big end and small end equal to 250 mm. 250 by 1000 equal to 0.25 meters. And stroke length is the LS, that is distance between TDC and BDC, top dead center and bottom dead center is LS, that is 120 mm. 120 by 1000 equal to 0.12 meters. Length of the crank pin equal to LC, suffix C refers crank, okay. LC equal to 52 mm, and the diameter of the crank pin DC, okay, DC equal to 36 mm. And thickness of flange or web for I section, for I section T equal to 4 mm, okay, that is 4 by 1000 equal to 0.04 meters. The density of the connecting rod material rho equal to 7800 kg per meter cube. Permissible bending stress in the rod, means permissible bending stress in the cap material and permissible bending stress in bolt material are same here. The capital A is the cross sectional area of the I cross section. I cross section is the cross sectional shape of the connecting rod, that is 11 t square. This is a 11 t square, okay. So here the value of thickness T equal to 4 mm, that is 0.004 meters. So 11 into 0.004 whole square equal to 1.76 in 10 to the power minus 4 meter square. Mass of the connecting rod. The mass of the connecting rod equal to density of the connecting rod into area of the connecting rod into length of the connecting rod. Okay, same as whipping stresses problem. Okay, and the value is 0.3432 kgs, and angular velocity omega equal 2 pi n by 60. That is the angular velocity of the crankshaft. Okay, so angular velocity of the crankshaft omega equal 2 pi n by 60. N value is 1500 rpm. Okay, so speed of the engine equal to 1500 rpm. So the angular velocity of the crank equal to 157.0796 radians per second. Here this is the angular velocity. So the units for angular velocity equal to radians per second. Okay. Permissible tensile stress in bolts for bolt materials and connecting rod cap material having bending stresses and tensile stresses as 100 megapascal. Okay, radius of the crank radius equal small r equal to here the small r equal to length of the connecting rod by 4. Okay, the length of the connecting rod equal to 0.25 meters, so 0.25 by 4 equal to 0.06 meters. This is the radius of the crank. Okay, by using these details you have to design a suitable size of bolt. Okay, this is the thickness here. This is TC is the thickness of the cap, BC is the width of the cap, okay, and X is the distance between the bolts. Okay, X is the distance between the bolts. First of all, you have to determine the inertia forces acting on the bolts. Okay, the formula for inertia forces acting on the bolts equal to pi by 4 d square and sigma t into nb. Here dcb whole square. Dcb is the core diameter of the bolt. dcb is the core diameter of the bolt. Okay, and sigma t is the tensile stress for bolt material. Okay, that is 100 mm, 100 megapascal is given. And nb is the number of bolts. Nb is the number of bolts used for a connecting rod. For connecting rods, so we are using only 2 bolts. Okay, 2 bolts and 2 nuts. So nb equal to 2. Okay, and also here Fi there is another formula for inertia forces, that is mr omega square into r plus 1 plus small r by small l. Small r by small l, that is the radius of the crank divided by length of the connecting rod. Okay, by using these two formulas, you have to find out the value of DCB, that is core diameter of the bolt. Okay, here this is the another formula. Mr is the mass in kgs, where Wr is the weight of the reciprocal parts in newtons. Wr by g, W by G is equal to M. Okay, mass equal to weight by gravitational force. DCB equal to core diameter of the bolt, NB is equal to 2, number of bolts used for connecting rod equal to 2, and sigma T is the tensile stress for bolt material, that value equal to 100 megapascal is given. Mr is the mass of reciprocating parts, already given in a question. Weight of reciprocating parts, WR. Okay, so this is the bolt. Here you can observe the outside diameter as a major diameter or a nominal diameter, but DCB is the diameter of the core. Okay, that is the diameter of the solid shaft. DCB is the diameter of the core. Okay, so you have to find out this diameter of the core, DCB. Okay, so the formula for inertia force acting on the bolt equal to Fi equal to mr omega square into r 1 plus r by L. Okay, the mr value, that is the mass of reciprocating parts, already given in the question. Okay, and there is another formula for inertia force equal to Fi equal to pi by 4 dCb whole square sigma T into Nb. Okay, equating these two equations. Okay, so this is also inertia force, this one also inertia force. So you have to equate these two forces for getting the value of dCb. Okay, so here the mr value, r value, omega square, and capital L, small r, these all values already we know in given data. Here sigma T and Nb, these two values also we know, but dCb, diameter of the core diameter of the bolt, DCB, we don't know that value, so you have to find out that value. Substitute all values, mr, r, omega square, sigma T and Nb, then you will get the value of DCB. DCB equal 4.18 mm. Okay, DCB is the diameter of the core, DCB. Okay, after getting the core diameter, you have to find out the outside diameter, outer diameter or major diameter of the bolt, that is D equal to DCB by 0.84. Okay, that is nearly 5 mm. Okay, so the required diameter of the bolt equal to 5 mm. Okay, so the nominal diameter or outer diameter or major diameter of the bolt equal to 5 mm. Okay, ఈ సైజ్ ఉన్న బోల్ట్స్ 5 mm సైజ్ ఉన్న బోల్ట్స్ అనేవి ఇప్పుడు ఆ కనెక్టింగ్ వాటికి మనం యూజ్ చేయాలండి. అందుకంటే తక్కువ సైజులో ఉన్న బోల్ట్స్ యూజ్ చేస్తే కనుక మన వర్కింగ్లో ఫెయిల్ అయిపోద్ది. అదే మనకి 5 mm కన్నా ఎక్కువ వాడితే ఇబ్బంది లేదు. 5 mm కన్నా ఎక్కువ, మినిమం 5 mm సైజ్ ఉన్న బోల్ట్స్ వాడాలి. మినిమం, దట్ ఈస్ ది మినిమం రిక్వైర్మెంట్ అండి. ఆ ఫోర్సెస్ని తట్టుకోవాలంటే మినిమం 5 mm థిక్నెస్, 5 mm డయామీటర్ ఉండాలి బోల్ట్స్కి. ఓకే అండి. Now in this question you have to find out the thickness of the cap. Okay, so this is a cap. Here this is the thickness of the cap. Okay, already the values of width of the cap and width of the crank and length of the crank already given. Okay, and the x, here small x is the distance between the two bolts. Here this is a bolt and this is a bolt. Okay, the center distance between two bolts equal to x. X is the distance between the two bolts. Okay, so the length of x value is obtained from diameter of the crank, that is a DC, plus 2 into thickness, 2 times the thickness of the bearing liner, that is bush. Okay, bush, this is a bush, so thickness of the bush, that is I consider the thickness of the bush as 3 mm plus clearance. Okay, that means the gap between bolt and this bush equal to 3 mm, and nominal diameter of the bolt. Okay, this is the value of x. So the distance between the bolt centers equal to DC plus 6 mm plus 3 mm plus D equal to, this is the final formula for x. DC is the diameter of the crank plus 9 mm plus diameter of the bolt. Okay, D is the diameter of the bolt. Already we got the value of D, small d, and the DC value already given in problem. Okay, so 36 mm already given in problem DC value, and we got the value of a small d equal 5 mm. Okay, then small x equal 50 mm. Okay, 50 mm is the distance between the two bolts for this problem only. Okay, after getting the x value, you have to find out the compressive stresses acting on the cap. Okay, when you are joining this cap, here we are using bolts. When you are tightening the bolts, then compressive stresses are induced in the cap. Okay, that's why you have to find out the compressive stresses induced in the cap. Sigma c is the compressive stress, mc by zc is the formula for stress, bending stress induced in the cap. So bending stress, sorry, compressive stresses rather than bending stresses induced in the cap equal to mc by zc. mc is the bending moment in the cap divided by section modulus of the cap. Okay, bt square by 6 is the section modulus for cap, and mc is the bending moment in the cap. Bending moment in the cap equal to inertia force acting on the bolts into x is the distance between the bolts divided by 6. Already we got the value of fi. Okay, and x is the distance between the two caps, two bolts. Distance between the two bolts equal 50 divided by 6 equal this value equal to maximum bending moment, and substitute the value of maximum bending moment and the section modulus, then you will get the value of thickness of the cap. Thickness of the cap equal 5.14 mm. Okay, so TC is the, here you can observe this distance from here to here. From here to this value is TC. Okay, now the final step is whipping stresses. Okay, this is the formula for maximum stresses induced in the connecting rod. Mr omega square is the inertial force acting on the connecting rod. L is the length of the connecting rod. So L square by 9 root 3. This formula is for maximum bending stress, maximum bending moment. Maximum bending moment acting on the connecting rod. Okay, at the 1/3 length of the connecting rod, the maximum bending moment occurs. So this formula is for maximum bending moment for connecting rod. Okay, already we know the formula of mass of the reciprocating parts, and r is the radius of the crank, omega is the angular velocity of the crank. Okay, L is the length of the connecting rod. Okay, substitute all these values in this equation, you will get the value of maximum bending moment. That value equal 2.0369 Newton meter. Okay, after getting the maximum bending moment, you have to find out the value of section modulus for I cross section. Okay, I cross section zxx equal to 13.97 t power 3. This is the t power 3. So sorry, this is a t power 3. This one also t power 3. The thickness of the flange is given, that is 4 mm. So 0.004 meters whole power 3. So this is the value of section modulus, and already we know the formula for maximum bending stress equal to m maximum bending moment by section modulus. After substituting the values in this equation, you will get the value of sigma max. This sigma max is the maximum bending stress or whipping stress. Okay, here this is the induced stress in the connecting rod, but the value 100 megapascal given. Permissible bending stress is given, that is 100 megapascal. This is the maximum stress, but the induced stress is 2.2. That value is very less as compared to maximum stress. So the design of connecting rod and the design of cap is safe. Okay, okay friends, దీంతో మీకు టోటల్ కనెక్టింగ్ రాడ్ మీద 4 ప్రాబ్లమ్స్ అనేవి కంప్లీట్ అయిపోయినండి. సో డిజైన్ ఆఫ్ కనెక్టింగ్ రాడ్ అనేది టోటల్గా కంప్లీట్ అయిపోయింది. నెక్స్ట్ క్లాస్లో వచ్చేటప్పటికి మీకు క్రాంక్ షాఫ్ట్, డిజైన్ ఆఫ్ క్రాంక్ షాఫ్ట్ అనేది వస్తుంది. సో ఫస్ట్ నెక్స్ట్ క్లాస్ ఫంక్షన్ ఆఫ్ ఏ క్రాంక్ షాఫ్ట్ అండ్ టైప్స్ ఆఫ్ క్రాంక్ షాఫ్ట్స్ గురించి డిస్కస్ చేద్దాం. దాని తర్వాత ఇంకో క్లాసు డిజైన్ ప్రొసీజర్ అనేది ఒకసారి ఎక్స్ప్లెయిన్ చేసిన తర్వాత ప్రాబ్లమ్స్ అనేవి చెప్తానండి. క్రాంక్ షాఫ్ట్ మీద ప్రాబ్లమ్స్ కొంచెం పెద్దవండి, ఫార్ములాస్ కూడా చాలా ఎక్కువగా వస్తాయి. సో మీరు ఆ ఫార్ములాస్ అన్ని గుర్తు పెట్టుకుంటే డిజైన్ చేయగలరండి. ఓకే ఓకే ఫ్రెండ్స్, థ్యాంక్ యూ.